share the screen. Okay, maybe it's better look here. So we only have one section left, 5.5. Might as well make a mark here. So I'll introduce a little bit of it today, then the rest of the time I'll let you work on the quiz. I still have Monday and Tuesday to work on that. So I have today, Monday, and Tuesday to knock off our last section, 5.5. Okay, so we're still on schedule. Wednesday, our normal questions and answer session. Thursday's the last regular test. You know what to turn in, which is 4.9 to 5.5. Friday, I'll let you ask questions about previous exams if you have any. Okay. And our final is on Wednesday the 16th. We don't have class on Monday. We don't have class on Tuesday. Okay. It's final exam week that week, so check with your other teachers on what their final exam schedule is like. But for us, our final is Wednesday the 16th, 11:10 to 1:40. And if you say, how do I study? Just study the old exams. I'll pick problems that are similar to the previous exams. Okay. Now let's see, I usually give about 10 questions on the test, so the final probably be 15 or 20 questions is what I'm thinking. Okay, so let's see, we're gonna have 5 tests. So if 15 questions, it'll be like 3 questions from each test, and 20 questions, it would be 4 questions from each test, something like that. Okay. They don't have to be the very same questions, but questions that are similar to previous exams. Okay. All right, so I'm gonna introduce the last topic, which is on substitution, integration by substitution. It's kind of like the chain rule in reverse. And then after I feel like I've done enough problems, which is just 2 or 3, then I'll stop and give you the quiz. Okay, and that'll be it. All right, so 5.5, substitution. You can think of it as the chain rule in reverse. It's frequently referred to as a U substitution, because the normal letter we use for substitution is U. You don't have to use U, but that's what's standard in most textbooks, and most people do that. So a U substitution is what we normally call it. Okay, so this is the so-called substitution rule. Page 412 is where it starts. Okay, so let me give you the principle involved. All right, so look for a function and its derivative, or the derivative times a constant. Yes, right now it makes no sense if you've never seen this before. Go ahead and put down that idea. Look for a function and its derivative within the problem. You may not quite see the derivative, but you can multiply the derivative by a constant. Okay, it has to be a constant, not a variable expression. Okay. Then we're going to let u equal the function. Du equals the derivative of the function dx. That should be derivative, not derivation. Derivative. Here we go. Derivative of the function dx. Sure, right now you may say, I have absolutely no idea what you're talking about. But after you do several problems, maybe it makes a little bit of sense. Okay, so in the u substitution, we're trying to do the chain rule in reverse, essentially. If you see a function and its derivative, let u be the function. Du is the derivative of the function times dx. All right, so here we go. Number 1, first simple example, integral of cosine 2x dx. This one can actually be done a couple of ways. I'll show you both ways, which works for this one, but it isn't going to work for all of them in general. Okay. Cosine 2x dx. So option number 1 is, let's do it by the u substitution. After all, that's the topic of this section, u substitution. Okay. Now, I can make the problem simpler if instead of taking cosine of 2x, I just have cosine of u. Right? So I'll let u equal 2x. Right. What is the derivative of 2x? 2. Okay. I don't see a 2 anywhere, but that's okay. Okay. So first thing I'm going to show you is the notation. Now, with the Leibniz notation, Leibniz, L-E-I-B-N-I-Z, you don't even have to write that down if you don't want to. It's the D notation. We would write du dx equals 2, right? Well, imagine from here, if you multiply both sides by dx, it looks like this. Du equals 2 dx, right? So du dx equals 2. If I multiply both sides by dx, this cancels out. Du equals 2 dx. For this section, we're going to write it like this all the time. Du equals blah, blah, blah dx. Okay. So du equals the derivative of the function times dx. All right, so I'm going to replace 2 dx with du. Now, the original problem did not have any 2. It has a dx, doesn't have a 2. That's okay. I can multiply it by a constant. So I'll multiply by 2 inside the integral and by 1/2 outside the integral. Because 1/2 times 2 is 1. Okay, 1 is the identity of multiplication, meaning if you multiply an expression by 1, you get an equivalent expression. Okay, so I multiply by 1 in the form of 1/2 times 2. Now, 2x is equal to u. So the next step, I'm going to change it to cosine of u. And 2 dx is going to be my du. So I've changed the problem to 1/2 in front, cosine of 2x, that's now cosine of u, times 2 dx, and 2 dx is du. So I just substitute. I change u and I change du, so there it is. So I have 1/2 integral of cosine u du. Capital I is my notation for the original integral. That prevents me from having to write this all over again. Okay, I guess technically I'm supposed to write integral cosine 2x dx. Why write all that when you don't have to? So my notation is capital I will always mean the original integral. All right, so I have 1/2 integral of cosine u du. That's pretty straightforward. So what's integral of cosine? Sine. So 1/2 sine u. This is an indefinite integral, like section 4.9, so it needs a plus c. Now just change u back to what it was. What was u? 2x. So final answer, 1/2 sine 2x plus c. Right, so this is our first example of a u substitution. It's the chain rule in reverse, essentially. Okay. So look for a function and its derivative. I see 2x, whose derivative is 2. I don't have the 2, but that's okay. It's a derivative times a constant. I can multiply by 2. No big deal. Okay, so the original was cosine 2x dx. Let u be 2x. Du equals 2 dx. So we're not going to do this step here anymore. The Leibniz notation, Leibniz, was du dx equals 2. Multiply both sides by dx. We're going to generally go straight to here. If u equals 2x, du equals 2 dx. All right, I don't have 2 dx. I only have dx. So I put 2 inside, 1/2 outside. So now when I substitute, 1/2 cosine of u du. And there we go. Then I integrate. Integral of cosine u is sine u plus c. Change u back. It was 2x. So 1/2 sine 2x plus c. Final answer. Let's double check this. What's the derivative of this? The derivative of 1/2 sine of 2x, 1/2 cosine 2x, then by the chain rule times 2. That 2 knocks out the half, and you get cosine 2x. So it works perfectly. Okay, problem's finished. For this particular problem, there's another way to do it, just because there's constants involved. Okay, so the technique I'm about to show you now works for this problem. It doesn't work for number 5. It doesn't work for number 7, because it's not just a constant that you're worrying about. Okay. There's another way you can think of this, keeping in mind that integration and differentiation are opposite operations. Okay. Now, going back to the beginning, suppose I said, what's the derivative of cosine 2x? The derivative would be negative sine 2x, then by the chain rule times 2, right? Right, so keep that in mind. You're multiplying by an extra 2 when you differentiate. Well, since integration and differentiation are opposite operations, since you multiply by 2 when you differentiate, guess what you do when you integrate? Divide by 2. or multiply by half, right? So that would have been a lot faster in this case. You could just say, all right, I'll integrate sine 2x, and then I'll do the opposite of what I would have done for differentiation. Right? For differentiation, you would have said, oh, multiply by 2. So for integration, I will divide by 2 or multiply by 1/2. And so that also works. Okay. That works when that extra thing by the chain root is a constant. That's not going to work if you have a variable expression. Okay. So I'll show you number 5 now, which is a little bit different. Okay, so the original problem is integral of x cubed over x to the 4th minus 5 dx. Yes, I put other stuff in red. That's why I changed colors there. Okay, x cubed over x to the 4th minus 5. Look for a function and its derivative, or the derivative times a constant. Okay. Do you see a function and its derivative? Well, what's the derivative of x to the 4th minus 5? 4x cubed. I don't have 4x cubed. I do have an x cubed. That's going to be good. That's okay. Okay. If you don't quite see the derivative, but if it's a derivative times a constant, you're going to be good. Okay. So essentially, the derivative of the bottom is the top, except I have to put a constant in. But that doesn't bother me. Okay, so let u be x to the 4th minus 5. The derivative of x to the 4th minus 5 is 4x cubed dx. And again, notice the notation. Just write du equals the derivative dx. Yeah, the Leibniz notation would have been du dx equals that, right? Du dx equals 4x cubed. Multiply both sides by dx, and it looks like this. So we're always going to write it like this from now on. Okay, the next step, I'm going to write this as u. I cannot change to du until I see 4x cubed dx. Okay, the original problem has the x cubed, it has the dx, but there's no 4. But that's no big issue. Go ahead and put in the 4 inside, as long as I put 1/4 outside. So I've multiplied by 1 in the form of 1/4 times 4. Okay. I need to have the 4 because I can only change it to du once I see 4x cubed dx. 4x cubed dx. Okay. Now I've circled this. The next step, that's going to be my u. 4x cubed dx. I now have 4x cubed dx. Change that to du, and this is u. So I now have the integral. I stands for the original integral. 1/4. The numerator is 4x cubed dx. That's du. Divided by x to the 4th minus 5 is now u. And there we go. All right, so that's my natural log. Remember, you can pretend there's a 1 here. Maybe I can just sneak it in if you want. Du over u is like 1 over u du. That's natural log. So 1/4 ln absolute value of u plus c. Careful, don't forget it's absolute value in general. Not just ln u, absolute value of u. And then change u back to what it was, x to the 4th minus 5. So final answer, 1/4 natural log absolute value of x to the 4th minus 5 plus c. And there we go. Okay. You can double check by taking the derivative. Okay. Let's do that. Of course, you know the derivative of any constant is 0, so that's easy. What's the derivative of 1/4 ln absolute value of x to the 4th minus 5? You have 1/4 1 over x to the 4th minus 5. So there it is on the bottom, right? X to the 4th minus 5 on the bottom. Then by the chain root times the derivative of the inside, which is 4x cubed. 4 cancels out to 1/4. And you still have the x cubed on top. There it is. So it works. It's perfect. Okay, so this is sort of the chain root in reverse, okay, by means of a u substitution. So look for a function and its derivative, or maybe the derivative times a constant. If you don't quite see the derivative, but you can multiply the du expression by a constant, that's still going to be okay. All right, I was going to show you number 7, and that's it. Okay, I was going to stop at 7 and go ahead and give you the quiz, which is on definite integrals. Okay, so here's the original. So temporarily ignore all the red and the green stuff. The original was x radical 1 minus x squared dx. Okay. So look for a function and its derivative. And a big tip-off is this is second degree, right? And the derivative of second degree is first degree. So that kind of tells you the way to go, right? This is exponent 2. The derivative will have just an x there. So that's the way we want to go. The tip-off here is fourth degree, third degree. You know the derivative of fourth degree will be something with third degree, right? The derivative of second degree, 1 minus x squared, will be first degree. We'll be off by a constant, but that doesn't bother me. Okay, so let this be u. U is 1 minus x squared. Du equals the derivative dx. So derivative of 1 minus x squared is negative 2x. Okay, all right. So let's compare the original with what I need. In order for me to switch over to du, I need negative 2x dx. What do I have? X dx. What's missing? Negative 2. As long as it's a constant that you need, it's okay. That doesn't work for variables, but for constants. So I need a negative 2 inside, multiplied by negative 2, and negative 1/2 outside. So in red, negative 1/2 here, negative 2 there. Now all of this stuff that I have in green is negative 2x dx. And you don't have to say, oh, they're not together. Multiplication is commutative, right? You can switch the order anytime you want. You can put the negative 2 in front and then the x and dx. So all of this is negative 2x dx. That becomes my du. And instead of radical 1 minus x squared, it's just radical u. So look at how much easier the integral is. Instead of radical 1 minus x squared, since 1 minus x squared is u, I'm taking the square root of u. And then negative 2x dx. Negative 2x dx changes to du. And yes, there's a negative 1/2 out in front. All right, so we know that's u to the 1/2. So integrate negative 1/2 times power rule, add 1 to 1/2 is 3/2. So u to the 3/2 divided by 3/2 means times 2/3 plus c, cancel, cancel. So that's going to be negative 1/3, and then just change u back to what it was. What was it? 1 minus x squared. So final answer, negative 1/3, 1 minus x squared to the 3/2 plus c. Final answer. And I was going to stop right there. So at least you've seen a little bit of how substitution works. Okay. So I'll do a lot more of these Monday and Tuesday. It's a little bit different technique when you have a definite integral substitution. I'll probably save that for Tuesday. Maybe I'll sneak in a little bit of that Monday, but we'll see how it goes. Okay, so I'll be doing a lot more of these kind of problems, but at least I've shown you a little bit of it. That's our last section, which is 5.5. Right. So I've just done very few. We got a lot more to go, but I want to show you a little bit of that. Okay, so I'm ready to start the quiz unless anybody has a quick question about something. Let me check the chat. Okay, grading for the final exam. So the final exam, you'll get a score between 0 and 100, just like all the others, and you pretend you get that same score 3 times. So it's just like you're taking 3 tests. Okay, so you'll have 8 tests, then out of those 8, you can have 1 dropped. That's the way the final exam works. Okay, so when you take the final, it's equivalent to taking 3 100-point tests. Okay, and you get the same score on all of them. So if you get a 90 on the final, it goes 90, 90, 90. If you get 100 on the final, it's 100, 100, 100. Okay, so you'll have 8 scores, and then you drop 1 of those. Okay. All right. Any other quick questions anybody wants to ask? Let me check the chat. Otherwise, I'll send you to the quiz. All right. I don't hear anything. I don't see anything. Okay. So get your cell phones out for the quiz, and as usual, I'll put you in your breakout rooms and do next class meeting, so Monday at 12:10, and have a good weekend. All right, so here we go, and show all your work. Okay, number 1, integral from 0 to 6, 2x cubed plus 7x dx. Number 2, integral from 0 to pi over 2, sine x plus cosine x dx. Number 3, integral from 1 to 5 of e to the negative x plus 1 over x dx. Okay, I know some of you just put something in the chat. I'll look at it as soon as I'm done with this. Okay, I'll hold this for another 10 seconds or so everybody get it. Next few seconds. If worse comes to worse, it should be on the video. It's still on the video. I'm still recording, but I'll turn off the recording shortly. Okay, hold it just a little bit longer. Hopefully you all have it now. Okay, so I'll set up your breakout rooms. Let me stop the share. The chat. Let's see. That. Okay, the previous exams were all there, hopefully. So yeah, you should be able to do that. Okay, so go ahead and get started. Let me set up your breakout rooms.